Hello everyone. So we're already done with the introduction of linear transformation. This time we're going to talk about properties of linear transformation. So just like in vector space, we also have properties of linear transformation to be satisfied so that we can say that the transformation is linear. So these properties will be used in identifying a linear transformation. So the first property says that the transformation of vectors u plus v is the same as the sum of the transformations of the two vectors. And the second one, the transformation of the product of the scalar and the vector v is also the same as the scalar times the transformation of vector v. But before we move on to that, let us first have these definitions. So T is a linear transformation, U and V are vectors, and C is the scalar. So if T is a linear transformation of vectors U and V, and C is a scalar, then these two following properties holds. So in this example, we're gonna try to prove that this is a linear transformation using the property of linear transformation. This is transformation from R2 to R3. So this is just an example of transformation, but this time let us just prove if this transformation is linear or not. So in this transformation, we have taken the transformed components of this vector by first getting its first component, that is x, minus the second component, which is y, and then adding the both components, and third, multiplying 2 by the first component. So that is the rule in this transformation. So if we're gonna assign numbers as components in this transformation, let's say 3 and 10. So if we're gonna transform this vector based from the rule of this transformation, so first we have to get the first component, that is 3, minus the second component, and then add the two components, that is 3 plus 10, and twice the first component, and that is the same as -7, +13, and 6. So this is just an example of linear transformation. So this is just an example of transformation based from this transformation. But our aim here is to prove that this is a linear transformation using the properties of linear transformation. So let us try to use the property. So in the first property, we have the transformation of the vector u plus v is equal to the transformation of vector u plus the transformation of vector v. So we're gonna prove if this transformation is linear using this property. So in this case, we are going to assign components of our two vectors, u and v. Okay, so I just have to rewrite so we can have more space. So in vector u, I assigned a sub 1 and a sub 2 as its component, and in vector v, I assigned b sub 1 and b sub 2 as its components. So using the rule in the transformation a while back, so let's write it. So this is now the transformation. So here, let us have the transformation of u plus v. So our u here is a sub 1, a sub 2, plus our v, that is b sub 1, b sub 2, which is also the same as the transformation of a sub 1 plus b sub 1, a sub 2 plus b sub 2. Sorry. Now let us try to apply the rule here in this transformation. So it says here that we have to get the first component minus the second component. So we are going to first get the first component and then subtract the second component from it. So that is a sub 1 plus b sub 1 minus a sub 2 plus b sub 2. And then next we have to get the first component and then add the second component. So that is a sub 1 plus b sub 1 plus a sub 2 plus b sub 2. And then the third one will multiply 2 by the first component. So that is 2 times a sub 1 plus b sub 1. And we know that this is also the same as a sub 1 plus b sub 1 minus a sub 2 minus b sub 2, and a sub 1 plus b sub 1 plus a sub 2 plus b sub 2, and 2 a sub 1 plus 2 b sub 1. And this is our t, or the transformation of vector u plus vector v. So we're gonna prove if this is the same as the transformation of vector u plus the transformation of vector v. So as you can see, we left our answer in our first term, so we're done with this. Now let's try to apply this one in our transformation. So having the same components of our vectors u and v, we will try to apply the rules in this transformation in the transformation of u plus transformation of v. So that is the transformation of a sub 1, a sub 2, plus the transformation of b sub 1, b sub 2. So applying this, we'll be having, of course, the first component, that is a sub 1, minus second component, which is a sub 2. Again, the first component, a sub 1, plus the second component, a sub 2, and we have to double our first component, so that is 2a sub 1, plus, so we have b sub 1 minus b sub 2, b sub 1 plus b sub 2, and twice b sub 1. Okay, so that is also the same as, we're going to combine this, that would be a sub 1 minus a sub 2 plus b sub 1 minus b sub 2, and a sub 1 plus a sub 2 plus b sub 1 plus b sub 2, and we have 2a sub 1 plus 2b sub 1. So that is equal to the transformation of vector u plus the transformation of vector v. So we'll check now if this is the same as the transformation of the sum of the two vectors. Okay, so we have a sub 1. We also have negative a sub 2, positive b sub 1, and negative b sub 2. We have a sub 1, b sub 1, a sub 2, and b sub 2. And we have 2a sub 1 plus 2b sub 1. We have 2a sub 1 plus 2b sub 1. So we can say that, or we have proven that this property is true. And this transformation is linear. So let us see if the second condition will also be satisfied. So as usual, vector u is equal to a sub 1, a sub 2. So if we're going to take this property, so this would be the transformation of the scalar times a sub 1, a sub 2. And we know that this is also the same as transformation of C a sub 1 and C a sub 2. So now we're gonna use this rule in this transformation. So that would be the first component, which is C a sub 1 minus C a sub 2, C a sub 1 plus C a sub 2, and twice C a sub 1, or twice the scalar times a sub 1. Now let's take the other term. So that's the scalar times the transformation of vector u. So let's see if we will get the same components that we got with the transformation of the scalar times vector u. Okay, so that is C, or the scalar times transformation of vector u, that is a sub 1, a sub 2. Or this is the same as the scalar times the transformation of vector u. So using this, we're gonna subtract the second term with the first term. So that is a sub 1 minus a sub 2. Then a sub 1 plus a sub 2. And then 2a sub 1. So multiplying the scalar with the transformation of vector u, that would be, so that is C a sub 1, or scalar times a sub 1 minus the scalar times a sub 2, scalar a sub 1 plus the scalar a sub 2, and 2 scalar a sub 1. And that is the scalar times the transformation of vector u. So what did we notice? So we noticed that they have the same components. So that means that the second condition was satisfied. Well, actually, some of the discussions about linear transformation includes the zero vector as one of its conditions to prove that a transformation is linear, but then the two conditions are already enough to prove that the transformation is linear. So now it's your turn to prove that this transformation is linear using the two conditions or properties of linear transformation.